Okay, so today we're going to do a lot of recap from last week's lab on Thursday. So if you guys remember, you took a bolt, huh? I see what you're saying, yeah. That's okay for today. You took a bolt, you boiled it, okay? You got to 100 degrees, you tossed it into a cup, a double insulator cup with some water in it. You got the temperature before you put the bolt in. Once you put the bolt in, you switch it around, you got that temperature. And we calculate the specific heat capacity, that is the C of your bolt. Now, what we did was we used a Q to Q strategy, which we're going to go through here again in a minute. These problems are tough, but I do expect you to be able to do this on your test. Now, your test is on Thursday and Friday. It's too long of a test to make you guys try and do it in one period, basically. So we spread it across 2 days. So we split into 2 halves. So it's not like you'll get the whole test on Thursday, and then whenever you don't finish, you'll finish it on Friday. It's like you get part A of the test on Thursday, and you only have Thursday to do it. Then on Friday, you get part B of the test, and you only have Friday to do part B. So you can't start part B early. You can't continue to work on part A on Friday, that kind of thing. Does that kind of make sense? So that'll be Thursday and Friday. We're not learning anything new between now and the test. So it's all review stuff. Monday, Tuesday, Wednesday, we're just reviewing, so nothing new at this point. So I want to make sure you guys can do a lot of the tougher problems that are going to be on that test. A Q to Q would be one of the skills that you'll definitely need. So right now, make sure you pop out your headphones. You will have a time where you're sort of practicing on your own, where you can kind of put one headphone in while you're working. But let's go through this. So this lab, this is some data we collected. Instead of a bolt, so instead of a bolt on a string, so instead of this guy, we have pennies on a string. And we're trying to calculate the heat capacity of our pennies. So here are your original numbers. So we got the mass of the empty cups. We know the mass of the cups with water in them. We know the mass of the pennies. We know the initial temperature of the water. And we know the final temperature of the water. So those are numbers that you would have to collect on your own while you're doing a lab. But those are numbers I'm giving to you. They're printed on your paper. Okay? Because we're pretending like you had done this lab. We're pretending like you had done this lab. So first things first. All right, we have the mass of the cups when they're empty. So these cups when they're empty. And we also have the mass of the cups with water in them. So what is the mass of our water actually going to be? How do we calculate that? Difference of the what?
Cups, empty cups, water.
Yeah, so we want to find the difference between these two, okay? Because one's got the cups by themselves and one's the cups with the water in them. So you want to find the difference between those two. I'll wait till someone can calculate that for me. Let me know what you get.
69.
What do you want us to subtract?
I mean, 59.
59.1, yeah. 59.1. And we found a difference between those first two numbers. And the reason why we chose those numbers was because 68.35, that is the mass of your cups with water in them. And the mass of your cups all by themselves is 9.25. So if we subtract the empty cups, we'll find out the mass of the water that's actually in there. Does that kind of make sense? Okay. All right. Now here's what happened. The water was at a pretty low temp. It's all the way down here. The pennies, here, let's go back to the bolt lab for a second. Hey, right when you pulled the bolt out of the boiling water, did you guys want to touch it? No, why not? It was really hot. How hot exactly? It's 100 degrees. Because it was in boiling water for 5 minutes, and the temperature of boiling water is always 100 degrees, right? So the metal starts off at 100 degrees way up here. The cold water was starting down here somewhere. It was usually close to like 20 degrees. When you put them together, the water temperature goes up, the metal temperature goes down, and they meet somewhere in between their starting temperature. So the penny started up here somewhere, 100 degrees. So you guys will all have 100 degrees. The water's initial temp, so that's just this guy right here, is 19.9. And they met somewhere in between. In this particular case, that is 25.8. That's 25.8. So what's the delta T of my metal? What's the delta T of the metal, the pennies in this case? What's their change in temperature? Yeah, of the metal. What's the delta T of my metal here? Somebody talk to me about that. Michael, how did you get the change in temperature of the metal for this one?
You got it, down to 4.2.
Subtract. Okay, you're right. You are going to find a difference of something. So, what's that?
The ones you circled.
So these are both for the water. So we actually are going to use that, but not right now. If I'm talking about just the pennies there. So Michael, what temperature did?
Those, like right there, like the ones that.
Say the numbers. What numbers? So Michael, what temperature did the penny start at?
19.
What was their initial temperature? The pennies.
That's the water, right?
That's the water, right?
100.
Yeah, a 100 because. So Michael, remember when you pull the bolt out of the boiling water? It's at 100 degrees right when you're pulling out the boiling water. Does that kind of make sense? So it starts at 100 and it goes down to this final temp, that 25.8. So Michael, how are we going to calculate the delta T? What do we need to do? What numbers are we plugging in?
You gotta subtract the initial and the final time. Those two, right?
Right, so which two numbers are you talking about?
100 and 20.
Yeah, you got it. Yep. So go ahead and plug that in for me. Tell me what you get. So we're going to find a difference between the two temperatures of the metal. So the metal was at 100. It went down to the 25.8. And so Maya, what would you do if you wanted to find the temperature, change the temperature of the water? Subtract which two?
Find the temperature of the water, and it's something to do with like the initial temperature.
Yeah. It's just here's the water went up to 25.8, but it started at 19.9. So we just want to find the gap between those two. Yep. Hey Mike, what did you get for the delta T of the metal?
74.2.
You got it. Love that. Okay. And that's coming from these two right here. Ooh, these two guys. Now over here, the difference between those two, that's how much the water changed temperature. So that's going to be your 5.9. And that's where I did 25.8 minus 19.9, which is what Samaya was kind of talking about. Okay. Now here's the big idea. Here's the big idea. I'm going to highlight this. The Q of the water was the Q of the penny. In other words, the amount of energy the water gained, because it went up in temperature, is the exact same amount of energy that the metal lost. On Thursday, that was a bolt. Today, this is a penny. Okay? So the penny basically, because it's really high temperature, you put it in the cold water, it starts throwing heat into the water, and the water starts receiving heat. So however much heat the penny loses, that's the exact same number as the water gains. So the Q of the water is going to be the M, C, and delta T of the water. So think of these as two sides of a fence, okay? So on the left, the Q of the water is the M, the C, and the delta T of the water. On the right, the Q of the penny is the M, C, and delta T of the penny. So just be very careful. So what is the mass of my water on the left? What is the mass of my water? Yeah, it's 59.1. We're getting that from our data. That's just this guy up here. What is the C of liquid water? The specific heat capacity of liquid water? 4.18. That's the one number I always tell you guys, 4.18, 4.18. Yep, so that's 4.18. And what was the delta T of the water that we just calculated? 5.9, yep. So this guy is the one that goes here. All right, now we're on the other side of the fence. Other side of the fence. What is the mass of the penny? What is the mass of the penny?
49.5.
Yeah. So that's how we're using a 49.50 here, not the 59.10 anymore, because we're talking about the mass of the penny. Mass of the penny. Do we know what the C of the penny is? No, that's what we're looking for. Remember I wrote it up here? We're looking for that C, the heat capacity. So that's the one variable we don't know, so I'll just leave it as a C. I don't know what that is. And then Jason Martin, talk to me about the delta T of the penny. What's that? Yep, you got it. So we're just using this guy right here. That's why we calculated it earlier. That guy goes there. Boom. Alrighty. So we got our two sides of the fence. So 59.10 times 4.18 times 5.9. That will be equal to the amount of energy, the Q that your water gained. That will be equal to the mass of the penny times the C of the penny times the delta T of the penny. That's how much energy the penny lost. All right. So if we simplify this, 59.10 times 4.18 times 5.9, that comes out to be 1,457.52. Will someone plug in what 49.50 times 74.2 equals? Someone plug that in for me. 49.50 times 74.2.
3,672.
There we go. And I'm going to just multiply that by C still. So I just kind of simplified things a little bit. Now, I want C by itself. Currently, it's multiplied by 3,672.9. So what do I need to do to get C all by itself? Yep. Divide by 3672.9. Gotta do the opposite. Here we go there. So these guys will cancel out. What is 1,457.52 divided by 3,672.9? What is that? Should be number less than 1. 0.39. 7. So I was going to put that 7 on there. You could call it 0.402 if you want to round to 2 decimals. And what are the units for specific heat capacity? These are the goofy ones.
11.
Joules.
Joules over
Grams degrees Celsius.
McKenna's got it. Yep, joules over grams degrees Celsius. Nicely done, nicely done. And there's already a little box around it for you guys here.
Not 0.4.
You could call this 0.40 or you can call it 0.397. Either one's fine with me. Alrighty, so there we go. We got those. So on the back of this, if you flip this over, there's another lab that somebody did where they boiled the nail. So they did the exact same lab. You know, put the nail in boiling water for 5 minutes, get the temperature before, temperature after, all that good stuff. So I want you guys to see if you guys can do that problem on your own. So I'm going to give you guys several minutes. See if you can do that problem on your own. We will talk about it. I'm going to come around and I want to look at your guys' different papers and see what we got cooking, where we need a little bit of help. Because by the test on Thursday and Friday, you need to be able to do this kind of problem without my help, okay? So you need to be able to do this kind of problem without my help come Thursday or Friday. So I'm going to go ahead, if I were at home, you home folks, go ahead and hit pause now so you can go ahead and get cooking on this, and then we'll talk in a little bit. Now you've had some time to work on this. I'm going to sort of break down every step of this nail problem. Every step of this nail problem. So these numbers in red, those are given, okay? Those are given because that's what you would collect during the actual lab. Now, if this is the mass of my cup, this first number here, and this is the mass of my cups with water in them, what do I do with these two numbers to find the mass of just my water? Yeah, I want to subtract those two. So what did you guys get? 68.42 minus 8.76, what do we get? 89.66? Oh, okay. I was like, what? All right, she's lost it. Okay. Yep, there you go. 59.66. Okay. Now in this section, we're going to break it down. The initial temp of my water, that's already listed. That's right here. So that's just coming from right here, 24.5. The final temp of my water, just coming from right here, that's just data that you collect during the lab. That's nothing special there. Oh. It's 25.7. Okay, so if I want to know how much temperature my water changed, I'm going to find a difference between these two. Let's see here. Miguel, what did you get for the delta T of your water?
1.2.
Love it, love it. Okay, now this part is a little bit trickier, the delta T of the metal. So what temperature does the nail start at? What temperature does the metal in general always start at in these labs?
100.
100, because you boiled it for 5 minutes. Boiling water is always at what temperature? 100 degrees. Okay, so if something's in boiling water for 5 minutes, it's probably also 100 degrees. So the nail was at 100. It came down to that 25.7. And so its delta T is going to be a lot larger. Now, what did you guys get for the delta T there? For the nail?
74.2.
I got 74.3, I think. The other one was 74.2, so you might want to just double check that. All right, so then, yeah, you might just be on the other side there. So here again, here's the big idea. The Q of the tap water, so the water temperature goes up. The water temperature goes up because it gained energy. The nail temperature goes down because it lost energy. So these two numbers will always be equal. These two numbers will always be equal. What is the mass of your... Well, actually, one more thing before I start that. Now, let's just remember... I'll do this little guy over here. These, we want to split up the two sides of the fence. On the left, it's all about water. On the right, it's all about the nail. Okay? So let's see here. Warda, what is the mass of your water? Yep, 59.66. I'll do everything on the left in green. That is that right there, your mass of your water. Because it's labeled right there, mass of your water. Okay? Warda, what is the C of liquid water? That number is always 4.18. You could, before you even put your name on this handout, you can just write 4.18 right there because it's always going to be 4.18. The specific heat of water is always 4.18. And the delta T of your tap water, Warda? Yep. And that was just this guy right here. That was just this guy right here. That's where he goes. Okay, now on the other side of the fence. The other side of the fence. What is the mass of the nail? What's the mass of the nail? 3.71, yep. And I'll do the stuff on the right-hand side in black circles, boom. So that's this guy right here. 34.71. What is the C of the nail? We have no idea. That's what we're looking for, so we're just going to leave that as a C. What is the delta T of the nail? So, Jaden, I think you were explaining to someone how to calculate that. What did you get for your delta T of your nail? 74.3. You got it. And that is just this guy right here. Okay. That's why we calculated it earlier, so we can be nice and organized. So as we simplify this, 59.66 times 4.18 times 1.2. Luke, what did you get for that number? These three combined. 59.66 times 4.18 times 1.2. Okay, yeah, there you go. Kept a couple of decimals, that's great. Ian, what about you? We did 34.71 times 74.3 to simplify. If you haven't done that yet, go ahead and plug it into your calculator for me. Plug those two in, 34.71 times 74.3. Okay, I think that sounds about right. 2,578.95. Now just multiply that by C still. I need to divide both sides. So the opposite of multiplication is division. So we got to divide both sides by that 2,578.95. 2,578.95. These will cancel out. So I get C by itself, and 299.25 divided by 2,578.95 comes out to be 0.116. And what are the units again? Joules per gram degrees Celsius. There we go. We got a nice little box, so Mr. Pilcher knows exactly what to grade. Alrighty. So we're going to go ahead and transition over to this worksheet right here. So you guys can kind of pick where you want to start on these. So you can start on the front, you can start on the back. So these first couple, when you place a beaker full of water over a Bunsen burner, why does the temperature increase? So when you first get like the tap water, you just put it on there, the temperature starts going up right away when you put it on the flame. Why is that? You can draw, you can go with bullet points, numberless, full sentences. You can do a drawing of some kind over there. As long as it's labeled neatly, I can tell what it is. So there's a lot of ways to answer that. The next one is, why does the temperature of the water stop increasing once the water boils? So water always boils at what temperature? 100 degrees. And it'll just stay at 100 degrees no matter how long it's on that flame, right? Like it'll just stay on that 100 degrees. Why is that? Why is that? So that's something we talked about previously last week. So you might have to go back into your notes for that. With this guy, this is just a lot of labeling. So I can do like one or two of these for you, where we kind of go through, hey, right here, this is where your solid warms up. So phase change practice. This is where things are melting. If I'm going from left to right, and so on and so forth. So you guys have a nice chunk of notes over that kind of thing. So you can work on that if you want to. Or these are sort of similar to what we were just working on. But here's the thing. Calculate the specific heat capacity of metals. So this one is just another specific heat capacity calculation. You're looking for that C. This next one, you're given the C. So C is no longer a question mark. You know it. It's a given. And now you're actually looking for the initial temperature of the water. So I want to see if you guys can figure out, this would be a great example of a test question where you're using the same skills, but it's a thinker question because I'm asking you for a different angle. So if you want a real challenge, try that last one right there. You guys can choose what you want to work on. Start getting ready for your tests on Thursday and Friday. I'll be around to check in here in a minute. You guys can see the answer key below this video, or it's on your desk if you're in person. All right, folks, let's go get them. Yes.